before we get to Yukun's talk, which is going to be more specific about the foundation models work that we've done, I thought it'd be interesting to give you some high-level context about the work that we've been doing on AI and ophthalmology. And my hope is that there are some lessons or some points of interest for your own work in different areas. And Manas has been telling me about that just before this call. So we've touched on this already, but I wear a number of different hats. So I'm a consultant ophthalmologist at Moorfields Eye Hospital. Moorfields is the oldest eye hospital in the world and is the largest eye hospital in either Europe or North America. And at Moorfields, I specialize in the treatment of retinal disease. So in particular, I treat conditions like age-related macular degeneration, or AMD, which is the commonest cause of blindness in either the UK, Europe, or North America, and also treat diabetic eye disease, which is the commonest cause of blindness in people of working age. Now, I'm also a professor of artificial medical intelligence, and although I'm not a computer scientist and not an engineer, I've somehow come to find myself leading a multidisciplinary clinical research group that aims to develop and apply AI in healthcare using ophthalmology as an exemplar. And a key point is that we try to do early stage work going from an idea to an algorithm, but we also try to do later stage work going from code to clinic and clinical trials and implementation and health economics and so on. And so I think we've got a reasonably broad view of the pathways that are required. I'm very fortunate to be funded by UK Research and Innovation as a Future Leaders Fellow, and that gives me a lot of protected time for research as well as my clinical time. And then here's my financial disclosures. So in particular, given the nature of what I'm going to talk about, I've previously worked for a number of years as a consultant for DeepMind. So why do we need AI in ophthalmology? You know, aside from it's cool to publish papers and get grants, like what is the actual problem we need to address? Well, this is an image that I love to show when I'm talking to people from other medical specialties, because sometimes your cardiologists and your neurologists and your brain surgeons, they can sometimes think that ophthalmology is a small medical specialty or kind of a niche specialty. But in fact, since 2017, ophthalmology has overtaken orthopedics as the #1 busiest specialty in the National Health Service in the United Kingdom in terms of clinic appointments. So in fact, nearly 10% of all clinic appointments in England are for eyes. That's nearly 10 million appointments per year, and that's risen by about 37% in the last 5 years. And so if it's not too brutal a way to put it, we are drowning in the number of patients that we need to see. And this is a problem not just in the UK, but in Germany, in Europe, in the US, all around the world. We've got older, aging population, increased prevalence of diseases such as diabetes, et cetera, et cetera. And so there are these really tragic cases where people go blind because of delays in being seen and treated. And so this is an example from January 2020, just before the pandemic, where there was a young woman in her 30s in the south of England who was pregnant, and she had glaucoma and advanced glaucoma, and she needed to have some urgent surgery done. And because of delays in that happening for complex reasons, she essentially lost her sight. And if there had been earlier intervention, then this wouldn't have happened. And so that's just, I think, like a really tragic vignette which illustrates why I think we need to try and do things better. And so what I've come to believe is that new technologies and innovation can play at least some role in mitigating these challenges. But of course, I'm under no illusion that AI or machine learning is a panacea. And in fact, a lot of the time there are simpler and easier things that we can do that are often more effective than, you know, running a complex algorithm. So ophthalmology, I think it's fair to say, and of course I'm biased in saying this, but has been at the forefront of AI-enabled healthcare in many respects. So, you know, why do I feel I can say that? Well, the first ever autonomous AI system to receive FDA clearance is in diabetic eye disease from the company Digital Diagnostics. And in fact, the second ever entirely autonomous AI system to get FDA clearance was also in diabetic retinopathy. And that was in August 2020 for the company iNuke. Now, there are a greatly bigger number of devices that have received regulatory clearance in other specialties like radiology. But nevertheless, I think we're not doing too badly. Now, there's been a number of high-profile pieces of work in this space. So the Google Brain team in California developed a software called ARDA. They published it first in JAMA in 2016 for diabetic retinopathy screening, and that was one of the first examples in clinical medicine of using deep learning for a practical medical imaging task. And the nice thing is that we've seen that slowly but surely kind of percolate into use. And so this is a paper from the Lancet Digital Health that came out last year, which describes the prospective use of this algorithm in India and in Thailand. And I know from speaking to my ophthalmology colleagues in Aravind Eye Hospital in India that they now use the diabetic retinopathy tool from Google. They've used it in more than 350,000 patients. So it's nice to see the hype of AI starting to actually be translated slowly but surely into clinical practice. Now, having said all that, the fact of the matter is there isn't really widespread adoption of these systems. And so I'm sure many of you will have seen this very nice paper from Yukun Zhou and colleagues that came out in New England Journal of Medicine AI just a few weeks ago. And it was about the clinical adoption of medical AI systems. And they looked at it through CPT billing claims in the US. And so the nice thing about this paper was they actually looked at over 500 FDA cleared AI devices. And they looked at a database of over 11 billion claims between 2018 and 2023. And what was the upshot of that? Well, I can tell you that only two devices, two of those 500, had more than 10,000 billing claims. And that was for coronary artery disease and for diabetic retinopathy. And so, that's good for them, but it's still actually, even for the top two, it's a relatively minuscule amount of adoption as of yet. Now, my own involvement in this work really began in July 2016 when I set up a collaboration between Moorfields and the artificial intelligence company DeepMind. And of course, they need no introduction. I'm sure a lot of people have been following the announcement of Gemini earlier today, their new competitor for GPT-4 and other large models. But essentially, I approached them back in 2015 to see, could we develop a deep learning model that could look at these optical coherence tomography scans of the retina. It's kind of like OCT is a little bit like an ultrasound, but it measures the reflection of light waves rather than the echo of sound waves. And in doing so, it gives very, very high resolution three-dimensional images, much higher resolution than an MRI scanner or a CT scanner, for example. And so could we work together to develop a deep learning system to identify people with sight-threatening macular disease and prioritize them to be seen and treated? So in August 2018 then, it was really exciting because we were able to publish the first results of this work in the journal Nature Medicine. And of course, this being AI, you can't escape the hype around AI. And so it was exciting that it got widespread media attention, particularly in the UK. Prior to this, I published a lot of papers and put my heart and my soul into those papers, and they're probably read by like 5 people or 10 people. And so it's nice to be able to have your work reach a wider audience. At the same time, also quite awkward, because the fact of the matter is we haven't saved the sight of millions of people. And even now in 2023, the algorithm that we described in this paper is not yet in routine clinical care. And I'll talk a little bit more about that in a moment. So just to show you, this is the model. It's essentially 2 neural networks. There's a segmentation network and a classification network. If you look at the bottom row, we take an OCT volume scan, and the segmentation network will delineate between 10 and 15 different anatomic and pathologic features in the scan. You can see those in reddish orange, for example, in the 3rd row, and in blue on the 2nd row. And then the segmentation network feeds into a classification network, and the outputs of that are in the top left. And so in this case, it's recommending urgent referral to see a retina specialist, and it's doing a multi-class classification of what the diagnosis on the scan is. So where are we now in 2023 with this? Well, I thought I'd tell you a little story about this guy. His name is Ken Cukier. Ken is a senior editor at The Economist, and he was one of the people. He wrote this book called Big Data that I think was like one of the books that coined the term a decade or so ago. And he was familiar with our work at Moorfields with DeepMind, and I think he had written about it. And so what happened with him was that in the start of 2021, he developed sudden vision loss. And we were in the middle of a lockdown in London at the time. And so he sent me an email saying, like, what should I do? And so I was checking my email all the time. And so I called him up and I was able to talk him through the process of going into the emergency department at Moorfields and being seen and being treated. And so when he went in, he was seeing the nurses, seeing the doctors, and he was asking everybody, where is the world leading AI system that that I've heard so much about? And everybody was like looking at him and shrugging their shoulders and not really knowing what he was talking about. Now, a few days after he was seen and treated, he tweeted this. So he said, AI is a fraud. I went to Moorfields for emergency eye surgery, and instead of DeepMind's cool algorithms diagnosing me and robot surgeons, I had to accept the excellent skill, thoughtful care of human medical staff. What a disappointment. Now, of course, he was both praising us and teasing us at the same time. And as it happens, he had a condition which we wouldn't normally diagnose on an OCT scan, and therefore the AI system wouldn't have been helpful. But at the same time, he does make an entirely valid point. Why is this not yet in routine clinical use? And so just to touch on this, I think that it's clear that there's multiple challenges. And so, of course, there's publishing in your Nature Medicine journal and showing proof of concept that you get some state-of-the-art result or some other kind of benefits. But actually, beyond that, how do you do proper clinical validation? Does this require prospective studies, clinical trials, etc.? How do you get regulatory clearance? What sort of resources are required, and so on and so forth with that? But then actually the really kind of gnarly challenges most people haven't really engaged with yet beyond regulatory clearance. How do you integrate and deliver these models? And a crucial one, what's the business model? There are hundreds of AI startups in the healthcare space who don't really have a good business model or any business model. And without that, actually, it seems like success is going to be a challenge. And lots of other factors related to implementation and adoption. So I think that where we're at now is a little bit like the dawning of the electrical age. And so I like reading about Thomas Edison, and they talk about that September 4th, 1882 was when the electrical age began. And that was when someone from Edison's company was able to flip a switch and light up the Pearl Street district of Lower Manhattan. Now, the interesting thing about that for me is that actually for the 20 years before that, there was more than 20 different prototype light bulbs that often had similar designs to what Edison finally used, which is, carbon filament in a vacuum and so on. But actually, what Edison realizes, okay, first of all, you have to have something that's long acting. But actually, the bigger, I think, revelation was that you needed to have a lot of other things. So you needed to have reliable source of electricity, needed to have a distribution system, needed to have a connection system, needed to have a measurement system. And so it was a network of innovations. And I think at the moment where we are in AI and healthcare is still like producing a prototype light bulb that you show to a journalist and you say, isn't this amazing? Or you publish in a journal, and then you push them out of the room because 2 or 3 minutes later, the light bulb fizzles out. And we don't have the surrounding ecosystem to be able to take advantage of it. So the things from this collaboration, and I'll come to hand over to Yukun now in just a few minutes, but a few other things just to highlight is that because of this work, we were able to build an infrastructure within Moorfields for data aggregation and curation. We were also able to get a lot of expertise in information governance and data protection, and that's absolutely essential in terms of getting access to large-scale data. And then we also were able to develop computer science links within academia. So initially we worked a lot with DeepMind because we just had a brilliant relationship with them and they were really interested. But then we also were able to increasingly get top computer scientists from University College London and other places to work with us. And so in September 2019, we were able to get funding from the UK government to form something called the Insight Health Data Research Hub, which is an ophthalmic imaging bioresource. And so, we have got this continuously updating data pipeline. This is just a snapshot from one of our analytics dashboards. And we have over 20 million ophthalmic images with associated clinical metadata, and it's updating on a nightly basis. We can use that to generate anonymized data sets for research. And that was the basis of the RetFound work, which Yukun will talk about. The other thing that's cool is that we've got this cloud-based infrastructure. We can now take models that we develop or that others develop, and we can run it on the data pipeline. And so, for example, the system that we've developed with DeepMind, we've now run that on over 2 million historical OCT scans, and it runs on every new compatible OCT scan. And then all the outputs of the model go into our pipeline to enrich our data for further model development and other insights. And then an algorithm that Yukun has created is called Automorph, and this has run on over 3 million retinal photographs, and it does quality assessments, and it does retinal vascular metrics, and so on. So we're proud that we've developed the world's largest ophthalmic imaging bioresource. And then we're also proud that we have, I think, really gold standard governance processes around creating and giving access to anonymized data sets. We have a separate data trust advisory board that we created with the Open Data Institute, founded by Sir Tim Berners-Lee, so that we can make sure that we only do things where there's potential for patient benefit and there's no undue risk to patient privacy in any of the work that we do. Now, the other thing about this work is that it has allowed us to do a separate program of work completely independently from DeepMind because of what we learned about information governance. And so in particular in this area called oculomics, or using the eye as a window to the rest of the body. So we know now that with deep learning, you can look at a retinal photograph and say whether it's a man or a woman. You can predict their age, you can predict whether they smoke or not. You can even give a pretty good measurement of their blood pressure from a retinal photograph. And people got excited about that because there's a sense that there's a lot of extra biological information embedded within these high dimensional images that we as humans are not really cognizant of. And so because of the data pipeline we'd created and because of our expertise in information governance, we were able to do something called the ALTSI study. And so the ALTSI study is we got every patient aged above 40 who's had scans done at Moorfields, who's had ophthalmic imaging done over a 10-year period, and we got permission to link that data with a national database called Hospital Episode Statistics, which has the ICD-10 codes for every inpatient admission, outpatient admission, and emergency department attendance. So if someone has come to Moorfields, had an eye scan, and then moved to Liverpool and had a heart attack, we have that linkage, and we can use that to do interesting deep learning experiments. So, and if you're interested in this, we've got a cohort profile described in BMJ Open. So just to say some initial results, we found some interesting changes in the retinal vasculature and the retinal layers in patients with schizophrenia. And then just a couple of months ago, we looked at retinal changes in patients with Parkinson's disease. And the nice thing about the way we did this, that maybe have some relevance for your work, is that we try and combine the benefits of this ALTSI data set with other more deeply phenotyped data sets, such as UK Biobank. And so we were able to get about 700 patients in the ALTSI study who had Parkinson's disease, who also had retinal scans done. And we were then able to look at an incident, 53 incident cases of Parkinson's disease in UK Biobank that had retinal imaging done. And we were able to show subtle changes in the inner retinal layers, the dopaminergic layers, the internuclear layer in these patients. And this got a lot of attention because we saw some of these changes on average 7 years before the patients were diagnosed with Parkinson's disease. Now, of course, the media got very excited, and no matter how much we tried to tell them, we said, look, you can't use this to diagnose Parkinson's disease. This is finding subtle changes on average, across this population, but it still, doesn't necessarily sink in some of those subtleties. So the reason we're excited about the ALSI study is because really for me, the promise of AI is bringing world-class expertise out of specialized centers such as Moorfields into the community. And so we know in the UK that only about 9% of people between the age of 40 and 60 will go and have their NHS health check done. However, we know about 80% of people will go and have an eye test done. And so if we can pick up systemic disease from an eye exam, then that could have huge public health implications. So my last two slides, just to set the scene, to hand over to Yukun. So an article that I read in The Economist in July 2022 was talking about foundation models. And of course, this is something that I was conscious of, but it really was eloquently summed up in The Economist about how the progress in AI was accelerating. And I think everyone on this meeting is aware what an exciting year or so it's been, particularly since November 2022 with ChatGPT being released. And then, of course, alongside that, you had the sort of coining of the phrase foundation models, or the rebranding, or of this concept. And so the third part of what I said that we learned from the DeepMind collaboration was the links with the computer scientists. So we had the data infrastructure, we had the governance skills, and then being able to work with brilliant computer scientists, people like Yukun, was the real thing that began to allow us to venture into the field of foundation models. And then just before I hand over to Yukun, really just to emphasize, I do think that ophthalmology is one of the medical specialties that has the potential to be fundamentally transformed by AI. If anyone would like to get in touch with me, this is my email address, and I'm very happy to have emails. And if we run out of time with Q&A, very happy to be followed up later. So maybe I've talked for longer than I should have. I'll hand over to Yukun now to do the second part of this double act.
Thanks, Pearse. Let me share my screen. Yeah, let me take the second half. Thanks, Pearse, for your great summaries and the foundations for all the research for the AI in ophthalmology. And here I want to just take us through several some specific introduction and several points about the RadFont research. So first, I will quickly introduce the research motivations and some backgrounds about the foundation model research, then specifically focus on the research results and some analysis for the RadFont, and followed by several bullet points for the future research directions. So first of all, we know that data limitation is always a serious problem in the AI in healthcare research. It actually consists of lots of different complicated steps, including the ethic approval, data access, the identifications, quality control, and finally you get the structured data and you think about how to label them. And to be specific, some challenges about the AI in modeling regarding the data set experts. The first, we know that it usually requires a very heavy workload for the clinicians to do the annotation, especially when it comes to some large-scale clinical data sets, which involves in hundreds, thousands images. It's usually will be unrealistic for the clinicians to analyze all of the images or data. And the second point, the second challenge is about the application. So we know sometimes we have a new project coming and we recruit lots of clinicians, expertise to do the annotation. But usually when we have single categories of labeling or segmentation labelings, and then when we want to move to another new project, we probably need to think about how to do the new rounds of annotation for the new different disease diagnosis or for the different anatomic tissue segmentation. So this usually will easily introduce lots of like times of the workloads to the clinical workloads. And the third challenges is a gap in the development and the use case. So usually when we develop some AI models in a certain circumstance, so for example, let's say with some populations and the specific image devices, and then when we want to like use the AI models or deploy the AI models in kind of a different scenarios, usually with the different populations or image devices, we normally will observe a very like significant performance drops due to the difference in the training and in the validation. So these three challenges actually drives us to think about kind of uniform and effective solutions. And it naturally drives the definitions of the foundation model. So according to the RKL paper by the Stanford University, the Center for Foundation Model Research, they define the foundation model as any model that is trained on a broad data, generally using self-supervision and scale, that can be adapted, for example, using fine-tuning to a wide range of downstream tasks, plus some generalizability across multiple datasets. So if we just think about the three challenges in the last slides, it's actually the characteristic of the foundation model perfectly like solved or at least elevate the challenges. So for example, the first characteristic, self-supervision and scale, so which means the model can be theoretically trained with the image or data themselves instead of requiring a very heavy annotation workloads by the clinicians with activities. And the second characteristic is a wide range of downstream tasks. This actually can be a very important point because it actually help elevate the limitations in the single application. So if we look at, just to make an example, if we look at the foundation model as the roots of these trees, lots of different downstream tasks can be regarded as the different branches of these trees. So when you actually have a very good foundation model as a starting point, you can achieve a lot of, or you can train lots of different AI models for the different downstream tasks easily. And the third point is generalizability across multiple datasets. So multiple datasets usually consist of different characteristics like the population, demographics, and some image devices. While having a good generalizability across the multiple datasets will be super important and significant for the clinical use case. And according to another paper just recently published on the medical image analysis, it actually summarized the potentials of the foundation model in the different organs and in the different image modalities. This slide actually includes a screenshot, a graph from the RKL paper, which was handled on the RKL in, I think it's in the in last month. Yeah, so from this graph, we actually can observe like it is very like trendy or popular for the foundation model in recent 2 years. Just in the 2023, according to the 3 quarters, actually there has been already like more than 30 different foundation models in the medical fields. Some of them are about the text, some of them about the vision, and some of them is a combination of them. So in the following 2 slides, I will actually quickly mention why the ophthalmology, especially why the retinal imaging, is kind of a good starting point for the foundation model development or research. So the first thing is like in the ophthalmology, the image accumulation speed is very fast. So the left graph actually shows the retinal images collected by the Moorfields Eye Hospital. So we can see like back in 2017, it's already like collected more than 1 million retina images per year. And between 2022 to 2023, it collects more than 1.4 million retina images. So combining with the limited annotation resources, we naturally will understand that more and more retinal images has not been well annotated or labeled. So which means they're actually living somewhere in the hospitals without any contributions to the AI in ophthalmology research. So this naturally drives us to think about the self-supervised learning, just to use the images themselves to help build a kind of a powerful AI model. And the second characteristic about the retinal images is actually it has lots of different modalities. For example, the color funded photographs, ultraviolet, which actually show the peripheral areas of the macula, and also the optical coherent tomographies, which shows the anatomic different layers of the retina. So all of these different modalities actually provide the complementary informations for us to observe and understand the retina. And this actually builds the foundations for us to think about the multimodality research, at least from the vision sides in near future. And this part is actually some connection or links between the retina and the central nerve systems or cardiovascular system, as Pearse already mentioned it in the ALZI project. So I just skip this one. And then let's us to have a look at the rat-found research. So the rat-found research actually has two standardized stages. The first stage is self-supervisions on the retina images, and the second stage is actually the foundation model evaluations using a diverse downstream tasks, including the ocular disease diagnosis, ocular disease prognosis, and the oculomics, trying to predict the systemic disease with the retina images. So in the first stage, to train a foundation model with the self-supervised learning, we actually investigate the two different modalities. The first modality is called the color funded photographs, and the second modality is called OCT. For the color funded photographs, we collected more than 900,000 images. Well, 90% of them from the one internal dataset called MIDAS dataset. 90% of the images is from that dataset, and 10% is from Apex, a public available dataset in ophthalmology. And for the OCT, we collect more than 700,000 B scans for the OCT modality, and 85% is from MIDAS and 50% from the current dataset. So the reason why we, as you can see, like I would say the majorities of the images are from the Moorfields hospital. So the reason why we also trying to incorporate some public data is that we want to increase the diversity of the data representation, especially for the MIDAS inside the Moorfields. All of them are, naturally located at the UK. So by incorporating the IPACs, currently we can include some populations elsewhere, and also with lots of diverse image devices, which are, normally helpful for the models to learn the diverse representation. And to pre-process the images and do a little bit like quality assessment or quality control, we use Automorph. Pearse has also mentioned this software we actually developed in 2022 and made it open access. After the image pre-processings and curations, we start doing the model development and evaluation. So for the model development, we do the translational work, which means we adapt the advanced computer vision techniques to the medical field, to specifically to the ophthalmology. And we use the technique called master autoencoder, which was proposed by Meta AI, led by the group led by Kai Means. They proposed the techniques in 2021. And so the general idea for this kind of self-supervised learning techniques is actually using a retinal fundus photographs as an example. So first, you will crop the images into loads of square patches, and then you randomly mask a high proportions of patches, leaving only limited visible patches to the encoder, and then the encoder will transform all the patches to the feature vectors and deliver to the decoder. The decoder will try to reconstruct all the patches and then transform it as a whole the color fundus photographs. The training objective is just trying to reconstruct a color fundus photographs, which is actually the same with the original one without any masking. So definitely this is a super challenging tasks, especially when you mask a very high proportions of the patches. Intuitively speaking, like by training a model to achieve this task, the model has to learn like how to infer the masked information with the adjacent visible patches. So in this way, the model, we can call it to learn the retinal context or retinal representations by this kind of challenging training. So after the self-supervised trainings at scales on the MyData datasets and some public datasets, we just observed how the model can reconstruct the color fundus photographs and the OCT, the two different modalities. So as we can see on the graph, we mask very high proportions of the images, and we try to get the reconstruction results. So at the first glance, we clearly understand that lots of details like the textures cannot be reconstructed well. That's kind of reasonable because when you mask a very high proportion of it, it's really hard to restore the fine details. But a very inspiring and exciting observations is that we actually for those large anatomic tissues which are highlighted by the white arrows, the model has a kind of a decent reconstruction for those tissues. While the optic nerve head, the kind of large lesions and some large branch vessels surrounding the optic nerve head and the macula, all of these informative anatomic tissues. And for the OCT, we observe the similar situation is although it cannot reconstruction details well, but it still has a kind of a decent performance on the layer-wise structures and some kind of severe fluid lesion. After the first stage pre-training, we then start to evaluate if the models can really work in diverse downstream tasks, and how it performs with some test or analysis about the model generalizability, data label efficiency, etc. So to do that, we only need to keep the encoders and concatenate multi-layer perceptions for the classification tasks. So to do this kind of validation or evaluation, we try to include as much as public datasets as possible for the repeatability, and also because for the public datasets, it includes a diverse different diseases and from the different populations. So that will be a very strong evaluation for us to do. And for some of the tasks like the oculomics, trying to predict systemic disease with the retinal images, because there are no public data set for that specific task. So we include the internal data set called ALZI, also introduced by Pearse, and for the internal evaluation, and for the external evaluation, we use the UK Biobank. So we include several comparison baselines, like the models which was pre-trained with supervised learning on the ImageLab 21K, which includes 14 million natural images with their category labels. And we also includes the self-supervised learning strategies, exactly using the muscle to encoder, the same ones as what we use for the rat fonts. The only difference is on the pre-training data sets. So one we pre-train the models only on the natural images, and another ones we pre-train the model only on the retinal images. While for the rat font, we first pre-trained on the natural images and then followed by pre-training on the retinal images. This is just to highlight the contribution or importance of the pre-training on the different data sets or different fields. So this slide shows the results on the ocular disease diagnosis and the prognosis. So if we look at the left sides, all these the green subgraphs include each subgraph includes the results on one single public data set. Some of them are for the different disease, some of them are from with the same disease for the different data sets, like the diabetes, retinopathy, classification, glaucoma, multi-category, etc. So according to the comparison, so the rat font results has been highlighted with the darkest the bars, and comparing the performance with the most competitively baselines, we actually observe a significant improvement in, I think, in all of the cases. Yeah. And for the ocular disease prognosis, we use a wet AMD. So the task here is just trying to predict if the patient who has already been diagnosed as wet AMD on one eyes, if they will progress, to wet AMD for the fellow eye, which means the second eye, because wet AMD is kind of a symmetric conditions for the two eyes. And the task is trying to predict if the fellow eye will progress to wet AMD in the following 12 months. And we also observe the significant improvement. Here we evaluate the generalizability across the different data sets. So we still use the public data set here. And the target disease is diabetic retinopathy. So in each column, we try to fine-tune the rat font to one of the, there are 3 public data sets we use for the diabetic retinopathy classification. And in each column, we fine-tune the rat font on one of them, and then evaluates on the 2 other data sets. So by this way, we can actually comprehensively evaluate the generalizability across the different data sets. And we also observe a significant improvement in most of cases. So this slide shows the results about the oculomics. We try to investigate the efficacies of adapting the rat fonts to myocardial infarction prediction, heart failure, ischemic stroke, and Parkinson's disease. So the task here is incidence prediction, which means we actually trying to predict if the cardiovascular events or the neurodegenerative diseases will occur in the following 3 years. So which is also very challenging. According to the comparisons between the rat font and the most competitive methods here as the SSL retina, we observed a significant improvement. And also we then do the external evaluations on the UK Biobank. We indeed observe kind of a significant performance jumps compared to the internal evaluations on the outside data sets. This is because the difference in the populations and the image devices, because although the UK Biobank and the Moorfields Eye Hospital all located at UK, but usually only the patients who has moderate to severe diseases, ocular diseases, will be referred to the Moorfields Eye Hospital. So compared to the UK Biobank, it has kind of diseased populations compared to UK Biobank. And also for the image devices, the UK Biobank has used a kind of aged image devices, the Topcom 1000, I think. So there is a a clear difference in this different characteristic. But the results still show that rat phones achieve the best performance in most of cases. In this slide, it actually shows the data and the label efficiency, which means we try to use a different percentage of training data as shown in the x-axis, and we're trying to see like how it performs using the matrix AUROC. So the red lines indicate the results from the rat fonts. By comparing to the most competitive methods, you can see, for example, for the heart failure predictions and the myocardial infarction prediction, when the rat fonts only use 10% of the training data, it still can outperform or achieve the comparable performance to the baseline. And also we did the same analysis on the public datasets, the diabetes retinopathy classification. We can see that the rat font actually can save about 50% of the data. This slide shows some quantitative explanations. We use the heat map to highlight, especially for the models for the disease diagnosis, trying to highlight where the models looks at to make the final classification or prediction. So for the ocular diseases such as the myopia, diabetic retinopathy, glaucoma, the models usually just focus on the well-known and well-defined lesions like the atrophy, exudates, hemorrhage, optic nerve heads, etc. For the oculomics, including the ischemic stroke, Parkinson disease, myocardial infarction, usually the model will, on the color fonts photographs, the models will focus about on the optic nerve heads and some large vessel branches surrounding the optic nerve heads, as we can see in both cases, in all the cases. This actually echoes. So I want to highlight 2 points here. This actually first echoes the reconstruction map, because we actually observe that the model has a kind of a decent reconstruction results after the self-supervised learning for those large kind of large anatomic tissues such as the optic nerve head and the vessel branches, the large vessel branches surrounding it. And here they indeed contribute a lot to the classification, so which actually implicitly explains why the foundation models we developed, the rat font, can contribute to the different downstream tasks, especially for the systemic disease classification or prediction. And the second point is that this finding, this visualizations actually echoes with some of the association research that has been led by some clinician scientists in Moorfields, like Siegfried. They actually has been investigated the association between the different morphologies of the retina with the systemic disease. And we actually find the kind of consistent observations from the different research streams of research. And for the OCT, the model usually focus about the informative layers like the retinal nerve fiber layers, also macular areas, which are also has been verified as evidence or manifestations of systemic disease in the association research. So finally, we also look at the performance, the generalizability over the ethnicity. So we specifically look at the model's performance in the white, Asian British, black and black British. We basically observe a significant improvement brought by the rat font in the different ethnicities, although some of them has a different trend. So finally, some kind of a bullet points or plans for the short terms and kind of long-term plans. So for short terms, we definitely will try to keep adapting the rat fonts to diverse research. This involves wide collaborations with the external institute and researchers, because we actually want to challenge the rat fonts in lots of kind of a rare disease or some very different populations. And we also trying to think about the extension of the rat font to 3D. Like in the paper, and we will extend to 3Ds to fit with some image natures like the OCT volume. And we will also think about the multimodality framework for the foundation model. For the long term, we're trying to develop lots of diverse AI models so that they can be used for the early screening to identify some individuals with high risk of cardiovascular diseases or neurodegenerative diseases. And we hope the models developed can assist the clinical practice or used to select some cohorts for the clinical trials. And the important things I want to also highlight is that we actually also made the platform published available on the GitHub. And recently we have been working on the Google Colab notebook construction, and we will release it soon. Finally, I want to thank all the contributions and inputs from all the courses and the mentorship from my supervisors like Danny Alexander and Pearse Keane. And glad to answer any questions or receive lots of emails from all of you. Thank you.